Here are the notes for day 14. There's just 2 slides, and this looks like a whole lot of information, but if you follow along, it shouldn't be too bad. So we're going to be dealing with exponential growth models in day 14 and day 15. Day 14 is more the biological side of things, and day 15 is more the money side of things. So this is an exponential growth model, and to figure out what all these letters mean, here are the definitions. NO is the initial amount. It's the number at the beginning or times 0. K is called a growth constant, and e to the k is called a growth factor. Now, some books will have you solve for k. Other books will say solve for e to the k. I personally like e to the k better because I think it gives you more information. So that's why k has a red question mark and e to the k has a green exclamation point. If you're told to solve for k, do it. But if you're not told, I would suggest find e to the k instead of k. And you'll see this in an example in a minute. The variables are, an input is t and the output is n. So this is kind of like your x is your input and y is your output. But in this case, time is the input and n is the output, or the number or the amount of things. So with these equations, because there are so many variables, a lot of times you have to do them in a couple steps. The first step is to find either the k or e to the k. And you find that by using the initial amount. And then once you know e to the k or k, then you put those back into the formula to get your model where the only variables are the input time and the output n, and then you answer the question. So in this example, it says population of Arlington Heights was 74,652 in 1990, and then 75,175 in 2010. And they tell you to use time equals 0 for 1990. So I made a table and said in 1990, they told me to have time equals 0, and the population was this. And then 2010, which was 20 years later, so time is 20, population was that. And then the question says, find the population in 2014. Well, I know that I'm eventually going to use t equals 24. So to go through the 3 steps, first step is I need to use the initial amount to find NO. So I take 0, plug it in for t, I plug in an amount of 74,652, and then I realize that e to the 0 is 1, so NO, my initial amount, is 74,652. If your time is 0, then this number here is going to be the initial amount, NO, all the time. So now we can save the steps of solving this algebra and just call that NO. Anyway, once you have the initial amount, you go back to your model and you substitute in all the numbers that you know. NO is 74,652. Time for the purple information is 20 years. And then we have 75,175 is the number of people at the 20-year mark. So now if I divide both sides by 74,652, I have e to the k. In order to solve for e to the k, I raise both sides to the 1 over 20 power. That causes the 20 to disappear, and I get e to the k is 1.00055. So this is step 2. Well, actually, this is step 1. I've just found e to the k, and now I can go back and answer the question. NO is right there, e to the k is right here, and t and n are the 2 variables. The question said, find the population when t is 24. So I changed the t into 24. Do the exponential number first, multiply, and there's our answer. We predict the population is roughly 75,645 in the year 2014. So the second set of examples are using what's called a decay model. So instead of something growing, there's going to be decay, or something's getting smaller, and you still use this formula here. So again, I'm going to take the information and set up a table to organize what I know. The half-life of carbon-14 is 5730. Find the decay constant K in the decay model. So at the time 0, I don't know how much I have, but after 5,730 years, I know that I've got half of what I started with. So NO, the initial amount, is unknown, and 5,000 years later, we've got half as much. So when I plug those into the model, the amount that I have, 1/2 NO, after 5,730 years, even though I don't know how much I had, when I go to solve, divide both sides by NO, and the NO disappears. Now to solve for e to the k, I raise both sides to the 1 over 5730 power. E to the k is 1/2 raised to the 1 over 5730. You can use your calculator and you get this. So normally I would stop there, but the directions specifically said to find k, so now I have to solve this for k. Changing forms, log with a base of e of that 0.9998 number equals k. Using my calculator, I get k as an awfully small number, negative 1.29 times 10 to the negative 4. So here's my model. The amount is the initial amount times that k value raised to the t. Sorry, e to the k raised to the t. Okay, e to the k I found out was 0.999879, so I put this in here. You could say e to the k right here, but I think this is uglier and it doesn't have as much interpretation. This number here means that it's decaying because it's less than 1. So after my initial amount is multiplied by some number less than 1, my remaining amount is going to be smaller and smaller and smaller. So the last example is going to use carbon again. So the K number, or the e to the k that I found in the first example, is going to be moved over here. So I'm going to use it again. Estimate the age of a bone if it currently has 95% of it carbon-14 it had time equals 0. So at 0, again, I don't know how much I had, but now we're trying to find the time when 95% of it is remaining. So I need 0.95 of my original amount to be my amount. And I'm going to use e to the k from the previous problem. So again, start with your formula, plug in what you know. At time t, I have 0.95 NOs. I started with NO, and e to the k is this quantity here. Divide both sides by the NOs to make them disappear. How do we solve this? Change it into log form. Log base 0.9998 of 0.95 equals t. I'm going to use change of base to say log of 0.95 divided by the log of 0.999879. Plug that into my calculator. I get 976.3, so roughly 976 years. It'll have 95% of the carbon-14 it had at time t equals 0. So that's it. We'll go over any questions that you have in class.